Thanks for joining me for this webcast for the month of August. We've taken a little break from our normal monthly format for Geographic Calculator, but we're going to be starting that back up again. And this month we're going to be talking about georeferencing in Geographic Calculator. So a little bit of a look at our agenda for today. We're going to first look at a basic georeferencing example using control points. So sometimes raster imagery contains some sort of reference points embedded in the data, maybe reference marks on the actual image itself, or other information that you might have about those control points. So we can manually enter those coordinates in order to reference that data. In our second, more complicated example, we're going to look at georeferencing data using some kind of a reference. So if we don't know the actual coordinates of any of the features inside of our image, then we can match it up with some other existing reference data and create control points that way. We'll take a look at understanding and reducing the error in the model that we're using for georeferencing. And related to that is a little bit of talk about the different available georeferencing models. So the basic affine transformation that we'll see first is a straight linear georeferencing model. So we're going to connect points from the input pixel coordinates to our reference system using straight linear math. And then we'll look at some more complicated examples, cases where you might want to move into polynomial transformation methods. So start to apply some curves to that equation that goes from the original coordinate pixel values to our referenced coordinates. So before we dive too deep into the interface, let's just talk a little bit about exactly what we mean by georeferencing. So you can see in the image example on the left of my slide here, we've got a georeferenced image. So this was originally an historic map image that we'll actually look at in our second example. And this contained no spatial reference information, so it was just a straight square image. And in order to make it match up with other geospatial data, we need to apply some reference information to that data. And then, as a part of this process, typically transform that image so that the pixels actually line up with that reference system. So we're taking a map that is completely ungeospatially referenced, and using control points and some kind of an equation, we're going to transform that into a referenced image. So in order to start a raster transformation process, I'm going to go ahead and create a new job for my raster transform. So either using the start page links or the toolbar up here, I'm going to go ahead and create a new raster job. And first I want to point to my input image file. So this is a topo map. We're going to take a look at it in a minute, but it is a TIFF format. If there was reference information associated with this image, we would see this reference file information automatically fill in most cases. In this case, we have no known reference information associated with it yet, so we're going to go ahead and open the Georeferencer. You can also get to the Georeferencer from the Tools menu, but we generally recommend starting with a job so that you remember to actually transform your output data and not just save a reference file, which is typically only read by Geographic Calculator. So in my left pane here, I have my source data, so this is the topo quad that I just loaded. In the right side here, I have a second map pane where I could load some reference data. In this case, we don't need that. We're going to use the coordinate information that we can read off of our topo quad. So I'll go ahead and close this one. So we've got our topo image here. We've got some navigation tools up at the top. Let's go ahead and zoom in on the reference information here in the bottom corner so we can figure out what system we want to reference this image into. So we've got control points here. On the corners, we can see that we've got coordinates in geographic latitude, longitude numbers. If we read through this metadata information, we'll learn that the actual corners of our 7.5 minute topo quad here are in NAD 27. And then the reference marks, which are the dashed corner lines that are slightly offset from the actual corners of our topo tile, Those are in NAD83. So either of those systems would be possible to reference this image into. There's also some additional projected information listed here as well. So we have some Lambert conformal conics. So this is actually the state plane projection for Texas, which is the region that we're in. Those coordinates also exist on our topoquad. Any of those systems would be fine. Because the corners are in NAD27, and that will give me a nice clean output image with no margins. That's going to be the system that I choose to reference this image in, but any of those other systems would work as well. So the first thing that I want to do to set up this reference is to set that output coordinate system that we're referencing against, and right now it's defaulted to WGS84. So I'm going to go ahead and change that system. I don't need to do a limit by area, I'm just going to search, so I know this is in North America. I'll just search for NAD27 here. Okay. So I've set my reference coordinate system, and now I want to enter some reference points into this list. So before I add my control points to the map, I can see that my coordinate values here are listed as degrees and minutes, and I know from experience that the default when I first install the application is going to be in decimal degrees. So let's change that before we place any control points. So I'm going to go to the options menu and go to preferences. So right now in my reference point list, my geodetic coordinate format is going to be decimal degrees. If I enter degrees, minutes, seconds, it will convert it correctly to decimal degrees, but just to keep everything consistent so I can kind of see and match up with what I see on the map, let's go ahead and change that to degrees, minutes, seconds. I have some additional options as to how those coordinates are displaying in terms of showing positive or negative values or prefixes or suffixes with the cardinal directions. I'll just stick with this as it is here. I should be able to tell the difference between westing using the negative value here. That's not actually indicated on my map, but I do know that I'm in the Western Hemisphere. So we'll keep that negative. So this will change from decimal degrees to degrees, minutes, seconds in my control list. And I can always use the back button if I end up moving location here to get back to the view I was just at. And we're going to start with this bottom left corner here. So let me zoom into that location and we can add our first control point. So I want to use the Create New Reference Point tool, so it looks like a pencil at the end of my toolbar here. And I'm going to place my first point and try to line up those crosshairs right with the corner of that image. So you'll notice my reference point has populated with the source coordinates, the x and y, in pixels, and I'm going to go ahead and enter the reference coordinates in NAD27. So my easting value is going to be negative 94 degrees, 45 minutes, and my northing value is going to be 30 degrees. And when I'm happy with that, I can add that point to the list. So we're going to see that same x and y and the corresponding easting value and northing value. So that point looks good. I'm going to go ahead and add the next one here. So I'll move up to the top of my image. Let's add an overview map here. So in my window menu, I'm going to add an overview map. This is going to let me navigate a little bit more easily around the map. And we'll move to that top left corner here. And I want to place my next reference point. So I want to line up those crosshairs with that corner. And you'll notice that my source coordinates are updating. I want to update my reference coordinates as well. So let me just zoom out so I can read that information. So this one is going to be 30 degrees, 7 minutes, and 30 seconds. There's that 7.5 minute topo. And I can go ahead and add that point to my reference list as well. And we'll keep going with all 4 corners. So once we have our fourth point added, we're going to start to see some error information. So for this affine transformation, we need 4 points in order to be able to compare against a triangulated model. And that will start to give us some error information. So my x and y error and my x error and y error individually, those are in my source coordinates. So those are actual pixel units. So I'm seeing about 2 units of variation to transform all 4 of these values. And that makes sense given my data here. So if I zoom back into this corner, we can see just based on the resolution of this image, that line that I'm referencing to that I know the coordinates of, there's a little bit of variation of a couple of pixels here. So I can't really expect my error here to be less than, my known accuracy here within this data. So 2 is a pretty good value here. I'm pretty close to that, so I think I'm happy with my error in x and y here. My easting and northing error are going to translate into my reference coordinates. And in this case, because it's a geodetic system, it is actually converting that to meters. So this is a meters unit. If it were a projected system, it would be in the unit of my, my ground projected reference system. So that relates directly to my pixel values here. So my pixels are, a couple of meters, and we're seeing a slight variation here. This is a, 7.5 minute topo quad, fairly large pixels. So I can't expect super high precision here. I'm pretty happy with the numbers that I'm getting here, but I want them to be relative to what, my known precision is within my data. We can also take a look at the error plot for this data. So my overall root mean square error is under 3, which is great, just over 2. That's a pretty good error here. We are seeing some lines in terms of the direction that that's showing. So going from my source coordinates into reference coordinates, the predicted versus the actual modeled output coordinates, we're seeing that difference, and there is a large exaggeration here in order to show those lines across this whole area. You can also look at that in the reverse direction. So from the other direction, coming from the reference coordinate system and predicting what pixel location we'd be at, we're doing pretty well there as well. So we have fairly uniform distances here across these. That's one thing that we want to see. They're also not following an exact pattern. There's a slight kind of rotation here that we could look at shifting a couple of pixels if we wanted to get this even more perfect, but this is definitely within a good expected residual error. My maximum error here is about 6, so that's nice and low. So if I zoom back to my full data extent here, I can see that I'm doing a pretty good job with my error here. Let's take a look at what it might look like if one of my points were off. So this will also show how you would update a control point. So I'm going to take this last corner point here and completely relocate it. So let's update that much further east than it actually is, and we will replace that with 0.4. When we take a look at the error plot now, so in the forward direction, taking the observed pixel coordinates and modeling what they would be in geographic space, we can see that our RMSE has jumped way up here, much higher. So has our maximum residual. We can't quite identify which point that's related to yet because we only have 4 control points, so that makes it a little bit harder to tell. But if we start to look at this, we can see that this is a very regular pattern here. Something is wrong. Our further north values here are pointing inwards. Southern ones are pointing outwards. Something's off here. Very regular pattern in terms of the direction and also non-uniformity in terms of the distances. And then if we go back to our actual values here, we can see, so because there's only 4 points here in this affine model, there's not quite enough to use the residual error to identify which one is wrong. But we know just because of this error numbers that something is off here. So that would indicate that we'd want to go back and take a look at what our actual points are. We could also cut out points, so turn them off and see how that affects the error plot. And that will actually indicate that the one that is not being used in the model is getting shifted very far from the observed coordinates. So that's definitely the one that is incorrect. So let's turn that one back on and fix those values there. Zoom back into that corner. And we'll see our errors go back down. So at this point we've identified our 4 control points. So the next step is going to be to actually save those controls or complete the transformation process. If you did go straight to the georeferencing tool, this is the point where you would want to go ahead and create a new transform job using these data, or possibly also save the reference point. So we can save those to an RSF file that Geographic Calculator will recognize and use as a referencing system, but that's not a standard used in other applications. So in order to actually transform this data into a known geographic coordinate system, we want to transform the data and possibly resample those pixels to be inside of that coordinate system. So if we look in more detail at the reference point options, we can save that, so we can create things like a geotiff header, etc. However, that's not going to carry with it the transformation. That's just going to be the control points. And we want to maintain this affine transformation method to get from our control points into the known reference coordinate system. We don't want whatever GIS software we open the data with to handle that transformation. We want to make sure that we do it in the way that we expect. So we want to complete the transformation job. So I'm going to cancel out of this. We've set up our control points. We can go ahead and close the georeferencing window. And yes, I want to save the changes. And I also want to update the transformation job. So you saw those options in the file menu, but it will also walk you through it if you do just close the georeferencing window when you started with the raster transform job. So that has created a reference file that references our TIFF image. And we can see right here also the transformation model that's associated to take those input pixel coordinates and transform them into referenced coordinates. We also have some options to set the transformation area. So typically with images like this, we have this margin information, this additional data, and we might not want to use that. Since I did have control points right at the corners of the topo quad, I can actually output my image and crop it to basically the extent of just that map frame. So if I use my reference points, because they're on the corners in this particular case, I'm going to get just the actual map frame data. Or alternately, if I wanted to define an area that kind of cropped down to a smaller map area, I could do that as well. So then I need to set up my transformation here. So I could maintain NAD27, output this to NAD27. Just to keep this interesting, I think we'll output to NAD83. We can sort of see how the registration marks in NAD83 compare at the end here, just as a second check, just to see how we did here. So let's go ahead and pick a system for the output. And then we are going from one system to another, so we want a transformation method. And I need to set my destination file here. This raster transform job has a number of output file format options. I'll stick with TIFF. In this case, it is going to be a geotiff because we do have spatial information that we're adding to this data now. So we are taking input pixel coordinates using georeferencing to update that to NAD27, and then also applying a coordinate transformation. So we may also want to go in and modify the preferences here. We are using resampling. This is a image that is, line work and that type of thing. So this nearest neighbor is probably appropriate here to keep the color and just shift that to keep it orthogonal to the projection as our output. Let's go ahead and process this. So here's our output image. Looking at it inside of the viewer, we can see that it's in NAT83, and we can also, locate our cursor around the map and check any of these coordinates. Our second example is a little bit more complicated. I'm going to load in my TIFF image here. So this image was scanned into the computer. It's a historic map of North and South Dakota. And we've got a little bit of a preview here. We could also right-click on the image file here and open it in the viewer if we wanted to look at it in more detail. So this has no spatial information yet. We know that by this dialog, but this will let us preview it. So a few things about this image. So similar to the last one, we do have a map frame kind of contained inside of the image. And there are some coordinates. There is a bit of a coordinate grid. And this is, the northern edge of the United States. And we can see that this is a little bit of a curved line here. So this is that 49th parallel. And because it has that slight curve in it, we know that we're not in straight geographic projection. Unfortunately, on this image, we don't know from any of the metadata here what the actual projection used is. So it's not easy for us to guess. It's probably a ground projection. Because we see that slight curve, it's probably some kind of conic. But we're going to assume that this is an unrecoverable projection, and we're going to add control points using the actual features inside of this data as reference and comparing them to some known data. So we have the boundaries of the state here, of both of these states, some county boundaries, some state boundaries. We also have some water features. Those are typically not ideal for georeferencing against because, their location is not as fixed as some other things. But in a historic map like this, we don't need super high precision, and we've got to use what we have. So we'll probably look at the state, and then we might also need to bring in some hydrology as well. So going back to my raster transform job, I'm going to open the georeferencer. You can see right now we have no coordinate system associated with this image, so we know we need to georeference it and come up with some reference coordinates that will be listed as a reference file. So because there's no locations on the map that we can use, we don't really know any control points, and the coordinates here aren't really detailed enough for what we want. We're going to align control points on our image with some other reference data. So let's bring back the reference data viewer, and we're going to add some data to our right side map here. So I have some state boundaries here in geographic coordinates. These are in WGS84. This happens to be a map info tab file, but any of the vector formats supported I could have loaded in here. Obviously imagery would work as well if I had images that I want to line up against. So let's just set up our display here so we can see and navigate these layers a little bit better. So we're going to look at the upper left corner of the state here. And we want to look at the upper corner of North Dakota here as well. So using the pencil tool, I'm going to place my first reference point. And then in my reference data, also using the pencil tool, I'm going to place the corresponding control location within that reference data. And as I place those, I should see my coordinates update in my list. And then I can add that to my list of control points and they'll appear on the map. So I'm going to continue doing that for each of my corner locations here. And I can add an overview map to my reference data as well, just to help navigate. So if I wanted to use more meaningful names, I could always label these. So now that I've got a bunch of control points here, I can see I've started to get some residual error information. And I also went ahead and linked my two displays together so that I can easily navigate and compare the locations. So by comparing my two locations, I know that my curve in my image is not going to match with my geospatial data. I could compare it to the northern curve as well. Our source image here is curved and our reference data is straight. So this linear affine transformation is not going to appropriately line up this boundary with this straight line in our geographic coordinate system. I can't totally tell that from the error yet because I don't have any points interior. So let's add some additional reference data so we can come up with some points inside of this border. So we've got a county boundary here that's actually designated by a river. So I'm going to add some additional data here. So from the South Dakota State GIS, I was able to obtain some rivers and streams and lakes data, and we can use that to pinpoint this spot right on this boundary crossing. So I've also added a second point down at the southern border here. So taking a look at the error plot. So right now we're mapping linearly from these pixel coordinates into our reference data system. So looking at our error plot in the forward direction, our root mean square error is a little bit high here. Given the coordinate system that we're in and the scale that we're at, that's not terrible. Approximately similar magnitudes, a little bit of a pattern in the distribution, but it's not really until we look at the reverse error. So going from known geographic coordinates and predicting what the pixel location would be that we start to see a really high root mean square error here. So this is much too high for this data set. And we also have a fairly regular pattern here. So you can see because this original data is in a conic, we're starting to come in on the upper part of our data and go outwards on the lower part, and then also move down in the middle and up on the side. So that's matching kind of a curve angle here. We could imagine a curve going through here that might better fit these pixel locations. So this is a good case where an affine transformation is not ideal. I'm going to close this dialog here and let's change our referencing model to a second order polynomial. So this is going to fit a curve to our data. And if we take a look at our error plot now, much more random distribution in the reverse direction. So, and our root mean square error has gone down. Maximum residual, still reasonable given the scale that we're working at. And in the forward direction, So again, we've gotten our X and Y error down to within a couple of pixels. Given the resolution of this image and the line work that we're working with here, that's really the best that we can expect to do here. We've got, almost 5 pixels across these line work areas. So to accurately locate that boundary, we're going to have some variation there. And the equivalent of that in our actual projected space, so in meters, because of the scale that we're working at, that is definitely a reasonable error here. And if we remember from our metadata here, this is at a scale of 45 miles to 1 inch on the page. So of course we would expect, a few hundred meters of variation, within our predicted locations here. This is not a super precise map. Our error here is within an acceptable range. So I'm happy with these control points, so I want to make sure that I save them. So again, to finish this process and create a georeferenced image, we want to go back to our raster transform job. So we can see the transformation model that we're using here. We at this point have saved our reference points. So we have that RSF file that contains those points. So I need to specify an output. My pixel resolution is being automatically calculated, so that should be similar to what my original error was based on the number of pixel error I had in the image. So 1 pixel is about 240 meters once we transform to geographic space. Obviously it's measured in angular units within the actual coordinate system space, but we're getting an estimate of that in meters. So again, we may want to think about our processing settings here. Because we're taking a rectangular image that was a curved projection and transforming it into geographic, there are going to be some areas that contain no map pixel data. So we need to specify a background color. The default is going to be black. But here's where you would specify something else if you wanted that. We can specify what output file formats we want. This is a GeoTIFF, so I'm just going to stick with a GeoTIFF header. And some additional settings. And again, we're going from orthogonal to pixel grid to orthogonal to our geographic coordinate system, so there is some resampling happening. So we could specify methods depending on the input data type if it was necessary to recalculate some of those values. So typically with imagery, I want to maintain the same pixel value, and just as I shift and rotate that pixel and recalculate it, I just want to take the nearest pixel value rather than doing any type of averaging of the nearby neighborhood of values. And then we can process this. So we're in geographic space now. If I wanted to look at this in the context of my original data, I can add back in that reference data. So we've curved our original map to fit geographic coordinates here. And we've recalculated those pixels, so the ones at the edge that didn't contain any map data have gotten that background color. And we could check our alignment here just to make sure if we wanted to verify. And then we could also go back here and modify our settings and create a new output image. Thanks for joining me. If you have technical questions about the software, you can send them to geohelp@bluemarblegeo.com. Some more information on the screen also about downloading a trial version of the software, or information if you have any questions about ordering, contact our sales team. We'll return next month where we'll talk about navigating the geodetic database.